Hello Chem 1. Today we're going to start Unit 11, which is a look at gases, their properties, and how the measurements of pressure, volume, and temperature affect them. Let's get started. The first thing we want to do today is take a look at the properties of gases. What are some measurements we can take about gases? To start this, we need to take a look at something called the kinetic molecular theory. This is a theory that describes how gas particles move and behave when they're in an enclosed space. First, gases don't have a definite volume or shape. They take on the shape of their container, and you can change the volume by adding pressure and temperature. No intermolecular forces affect gas particles. Gas particles are colliding and bouncing off one another, and they don't have forces strong enough to keep them together. Also, gas particles are constantly moving in a random pattern. With solids and liquids, we have more organization, but gas particles are just colliding and bouncing off everything that's in their area. And they're moving really, really fast. The reason you don't feel them colliding into you, even in the room you're sitting in, is because they're so small that even though they're traveling that fast, you can't feel them colliding into you. Collisions between these gas particles is completely elastic. That means that when they collide, they don't lose energy. The average gas particle in this room, in the room you're sitting in, collides an average of 1 billion times per second. That means they're moving around with great speed and colliding into things a lot. And typically, the average kinetic energy, no matter how big the gas particle is the same as long as those gas particles are at the same temperature. So you can have a molecule of CO2 and a molecule of H2, which are different in size, but if they're at the same temperature, they're going to move with the same amount of kinetic energy. What that means is the smaller H2 molecule will actually be moving with a greater speed than the larger CO2 molecule. Alright, let's get into some things we can measure about gases. The first thing is density. Just like with solids and liquids, we can do mass over volume and figure out the density of a gas. And what you'll find is that gases are a lot less dense than solids and liquids. This should make a lot of sense because they take up really large volumes and they spread the particles way out. Another thing we can measure about gases is pressure. With solids and liquids, when you apply pressure to the outside of them, most of the time they're not going to compress or expand. But with gases, this is totally different. Because they have indefinite volumes, if I apply pressure to a gas, it will compress. And if I reduce pressure on the outside, it will expand. Pressure is a measure of force over a given area. The easiest way for you to feel pressure is just to stand on your 2 feet and focus on the pressure on the bottom of your feet. Now lift up one of your feet and you can feel the pressure on the bottom of your one remaining foot that's on the ground grow. That's because your mass hasn't changed, your force downward hasn't changed, but the surface area has been cut in half. And now the pressure that your body is applying to the ground has gone up. In gas, the pressure that we spend a lot of time looking at is air pressure or atmospheric pressure. We usually measure this in atmospheres, and typically at sea level the pressure is at 1 atmosphere because at sea level there's 1 atmosphere above that place all the way to outer space pressing down on that area. Just to summarize pressure here, as pressure increases, particles are going to grow closer together and take up less space. And if pressure decreases, particles are going to spread out and take up more space. You can see here with this graphic that down towards sea level, there are more air particles. That's because gravity is pulling air down toward Earth. Up at the top, you can see that we have less dense air. This is why when you get to a top of a really tall mountain, you have to really pay attention to air intake, because the air gets thinner, and so every time you breathe in, you're breathing in less molecules of oxygen. There are a bunch of different ways that we can measure pressure. Typically we measure them in atmospheres, but we can measure them in torr, psi, pascals, and millimeters of mercury. The reason we use millimeters of mercury is because the first barometer used mercury as the fluid inside. Torr and millimeters of mercury are actually the same, but the torr was named after the inventor of the barometer, which is Torricelli. You might have seen psi on your bike tire, your car tire, and pascals would be the SI unit for pressure. Typically in chemistry we're going to use atmospheres, but we could see problems with other units of gas that are being used. Because of this, you need to be able to convert across the different units of gas pressure. So if you look here, we have 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr, which equals 14.7 psi, which equals 101,325 pascals. These are just basic conversions, dimensional analysis. So if I'm going from 733 torr to atmosphere, I'm going to start with my given as I always do. I'm going to put torr down at the bottom and I'm going to put atmospheres up at the top. And then I just use my equality, 1 atmosphere equals 760 torr. and I take the 733 and divide by 760. So that'd be 0.964, and that would be atmospheres, and torr would cross out. In this next one, we've been given atmospheres. Atmospheres go at the bottom. We're converting 2 millimeters of mercury. I find my conversion, which is 1 atmosphere equals 760 millimeters of mercury. In this case, we're multiplying. So 1.34 times 760 equals 1018.4, and that's millimeters of mercury because the atmosphere is canceled out. When we start getting into the math of this section, converting different pressures is going to become important. That's all I really wanted to start you with today. Practice some of those conversions in your free time. We will see you soon.